Okay, so thank you everyone for joining today for this webinar. This webinar is organized by the IGCP 636 project, which is a research network supported by the UNESCO program. Today, the webinar is hosted by the University of Auckland, in particular from Professor Ellen Kaya and her students. These webinars are recorded and then we upload the recordings in the YouTube channel of our project. You can just look for IGCP 636 project on YouTube and you can listen to the recordings of this year, but also of past years. We started these online webinars in 2022. So you can find several useful information and geothermal overview topics in different countries around the world, since in this network, several countries are involved. So thank you for joining today. Thank you to Ellen, to your students, and the floor is yours. Ellen, please go ahead.
Let me share my screen first. Can you see my screen now?
Not yet.
Not yet? Okay, sorry. And now?
Yeah, now yes, full
Awesome.
screen.
Yeah, awesome. Where's my first slide? Kia ora, everyone. Good morning from New Zealand. Thank you for Daniela for inviting us to the project and for this webinar. And we are really pleased to have all of you here. And if I want to introduce myself, I work as a senior lecturer at the Department of Engineering Science and in the Geothermal Institute. I have a bunch of degrees like PhDs, MSEs, and diplomas in geothermal related areas and petroleum and natural gas as well originally. And I have more than 20 years of experience in research and commercial areas about the geothermal energy technology. My research areas are numerical reservoir simulation, reinjection strategies into geothermal systems, carbon dioxide reinjection, reactive transport modeling, gas-rich geothermal systems, pressure transient analysis. Since 2019, I've been working on supercritical geothermal reservoirs with a GNS-led project. It's called Geothermal Next Generation. I've been also co-leading a government-funded project in my team. I'm going to mention soon. In terms of governing roles, I've served for the International Geothermal Association as board of directors, and I chair the membership and nomination committees. So this talk is going to be, this webinar is going to be about injecting carbon dioxide into geothermal reservoirs and seeing the fate of this injected carbon dioxide in mineral forms or in gas form or in dissolved form. And my students, Vipap and Yevdomika, are going to be presenting their work. But before that, I'd like to give a background what's happening in New Zealand and in terms of our projects as well. So Aotearoa, New Zealand is taking significant steps in terms of addressing the climate change and related activities. So geothermal industry started to take steps as well. Like NAFA has been injecting 100% of their emissions to geothermal reservoir. Tehuka also has been doing it for 100%. And Natamariki injecting since 2021, 25% of their emissions. So these are New Zealand figures actually. As you can see, our emission intensity in terms of geothermal power generation is not that high. But there are some particular fields like Ohaki and Nafa. They have been releasing a bit more than the others. And these are some pictures from Nafa, Tehuka, and Natamariki geothermal fields. And in order to tackle this CO2 emission problems in geothermal fields, government also awarded us with $6 million project to work on for 5 years for this project. And our aim is to control mineralization of geothermal. In order to understand the mineralization perspective, we need to set up some numerical systems. So our scope is presenting a novel technology to enhance greenhouse gas solubility in geothermal wastewater, and also inject some agents which can induce the mineralization permanent trapping of this injected carbon dioxide. And we also aim to develop some framework and customize it for different type of geothermal power stations. Our vision and impact vision is to take this technology to expand it for more emission-intensive industries. So in traditional geothermal systems, we emit the carbon dioxide, even if it's a small amount, we emit carbon dioxide and other gases like H2S and nitrogen to atmosphere. But for this project, our suggestion is to capture this gas and dissolve inside an absorption column and inject some readily available chemicals and put underground as a research. Put underground. So for some of the geothermal fields, like the geothermal rock types in Iceland, it contains lots of calcium, magnesium, iron. So because Iceland is more rich in basalt, they have no problem with having mafic minerals in their geothermal systems. For example, when we inject carbon dioxide underground, when they combine with calcium, magnesium, iron, they precipitate in the carbonate form, or it can be sulfate form as well. If they are combining with H2S rather than carbon dioxide, it can precipitate as sulfate minerals. But in New Zealand, we don't have much basalt. Our rock types are usually greywacke, rhyolite, ignimbrite, and it is quite hard for making carbon dioxide to stick into this type of rocks. So in our project, we aim to inject some readily available chemicals to make the chemistry favorable for these systems to settle in the solid form. So for example, this is a picture from GNS. They had conducted some laboratory analysis to show how how carbon dioxide is dissolving some of the zones in the injection area and precipitating in different forms. So our project has 4 pillars. One of them is examine. We start with a laboratory scale examinations, then we expand it into larger scale numerical modeling and field implementations, and we are going to set up some pilot plant designs, and in the meantime we are going to contribute to policy development and some framework utilization. And we currently have been setting up a numerical experimental setup as well. So we designed an absorption column and a reactor and a corrosion chamber as well. And we have been doing some numerical modeling in the lab scale, feed zone scale, and large scale. So in the feed zone scale, we have worked in Tehuka, Rotokawa, Natamariki, and Nafa geothermal fields, and Mika and Mika and Waipaw are going to be talking about them soon. In terms of available positions, if you like to join our team, we had 4 PhD positions, but 3 of them has been filled. Mika has been granted with one of them, and we have 1 postdoc position available as well. In terms of international collaboration, we are certainly open to exploring additional international collaboration opportunities. And we also will be involved in the legal framework related to NCG permanent storage and long-term management and monitoring options. In terms of educational outreach and workforce development, which is ongoing, this is not limited to only university education. It also includes knowledge exchange and skill development with the indigenous Maori communities and wider New Zealand geothermal workforce. We are excited about creating a new collaboration with anyone who are interested as well in terms of commercial or research opportunities. So yeah, I'd like to give the floor to my students. Maybe if Tamika can start as well, because it's very early time in Indonesia, and I'm really grateful that he accepted to join us.
No worries. Thank you very much for this opportunity. So I'm first. Okay. Let me share my screen. Can you see my screen? Okay. Yeah. So good afternoon, everyone, and also good morning from here and to audience in New Zealand. My name is Mika. You can call me Mika, and I'm one of the students of Dr. Ellen Kaya. She's my supervisor for my master research project. And now I would like to present to you about my research that is related to the reactive transport modeling of non-condensable gas or NCG reinjection in Ngatamariki geothermal field in New Zealand. So this is just a little bit about me. I just graduated from Master of Energy in Auckland, maybe finished last 2 months, and this is just a little bit experience about me related to geothermal industry. And my current and latest work is as a geochemist for Star Energy Geothermal in Indonesia, especially for Salak Geothermal Field in West Java, Indonesia. And today I would like to talk to you first about the introduction of a little bit introduction about NCG injection and related to the Ngatamariki geothermal field, and then continue to research question methodology and the modeling scenarios that I created in this research. And I will show you two models that we created. The first one is the 1D radial model, and the second one is the 2D model. And this is the introduction. So geothermal is actually is a relatively clean energy compared to other energy, especially coal and other fossil fuel energy. And this low emission is mainly coming from the non-condensable gas or the NCG that can be decreased more by injecting the dissolved NCG back to the reservoir. And the practice to inject the NCG is actually possible to give positive impacts or negative impacts. One of the negative impact is the undesired changes in porosity and permeability, and this impact can be modeled or can be estimated by creating a reactive transport modeling. And related to the Ngatamariki geothermal field, so Ngatamariki geothermal field already have been injected their NCG since October 2021. So they mainly inject their NCG to NM9 injection wells and also to NM8 injection well here. And there is, if you can see, there is one of the nearest production well here in NM7. So this research want to know or want to model what is happening in the reservoir, and also what is the relation between the nearest production well in Ngatamariki geothermal. So the one and main research question is only one, is to know what is happening here in the reservoir, because they inject their NCG to the reservoir, and also from the same reservoir, they also produce their steam and brine to be flown to their binary power station. So we would like to know, is there any dissolution or precipitation of the minerals in the reservoir that may affect to the porosity and permeability changes in the reservoir? So as the methodology, we create and run the model using the EOS1 of TAF-REACT. And basically TAF-REACT is a simulation program to not only model the transport and flow, but also to model the reaction. So we call it as the reactive and transport modeling. So basically TAF-REACT is like TAF2, but with the capability to model also the geochemistry, the reaction. To use TAF-REACT, we will need several input files related to the mineralogy, geochemistry, and also reservoir data. The mineralogy data such as minerals volume fraction. So we will need to input how many percent of quartz, anhydrite, calcite, and other minerals to the model, and also the reactive surface area. And then related to geochemistry, we will need to input the reservoir chemistry, the injection chemistry, and also the chemical reaction related to the fluid and also the minerals reaction, and also other data such as reactive transport option and other. And why we need the mineralogy and geochemistry data? Because we want to solve this kind of equation here. So we want to know the Rn, whether the mineral is depositing or dissolving. And we can know the solution or the precipitation of the minerals by inputting the kinetic rate constant, the Kn, and also the reactive surface area and the saturation condition. The saturation condition it can be calculated based on the chemistry of initial and injection chemistry. Another data we will need the energy efficient that can be come from literature. Another input that we will need is related to the reservoir. We will need to create our model. In this research, we created the model using PyTaf for both 1D radial and 2D models. And also we will need the reservoir injection parameters such as pressure and temperature and other data. And then we input it into 3 different input files, the chemical input file, solute and flow input files, and we process it through TAF-REACT, and we will get the output files such as the mineralogy data, chemistry data, and other data, and then we can visualize it using the usual Microsoft Excel or PyTaf for the 2D visualization. And then this is the modeling scenario. So one of the goal in this research is to know to compare between different NCG injection scenarios. So the current condition of NCG injection in Latin America is they inject 25% of their NCG. So we would like to model this and also compare to if we don't inject any NCG at all in the field. And then one of the comparison that we want to create is also how about if we increase the NCG into 50% NCG injection. So we want to compare between 0%, 25%, and 50% NCG injection, and we model it since the before NCG reinjection, current NCG reinjection, and also future NCG reinjection towards more 10 years of injection. Now let's take a look first at the 1D radial model. So 1D radial model is important to know first conceptually about what is happening if we inject our NCG into the reservoir. So in this 1D radial model, I created the model of the first and largest feed zone in NM9, which is the main NCG injection wells in Ngatamariki. So I use the models parameter. I use the parameter of the feed zone to be used in the models. And this is just the imaging of the what is the 1D radial model that we created. And then as the results, overall the porosity, permeability, and also the minerals volume fraction is changes, and it is also related to the chemistry. Now it will be better if I just show you the results. So this is the porosity, permeability, and also calcite and anhydrite that I plotted towards the radial distance. So basically, we inject the NCG here, and also towards the right arrow. This is towards the further area from the injection wells. So basically, what we found in the model's result at the end of the model in 2034, the porosity is increased near the injection wells here, and since around 1,000 meters or 1 kilometers, the 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 porosity and also the permeability is decreased. So basically, porosity and permeability shows a similar trend. Why we observe porosity increase here and also porosity decrease in around 1 kilometers? It is because it is related to what is happening in the minerals, mainly the calcite and anhydrite. So calcite here near the injection well shows a dissolution trend, and also anhydrite here. And then after 1 kilometer, calcite shows a small precipitation trend, and also anhydrite shows a precipitation trend. So the trend that we saw in the minerals can be observed in the porosity and permeability trend. And one of the things is related to the comparison between different scenario, 0%, 25%, and 50%. It is not not clear the difference between these scenarios in porosity, permeability, and anhydrite trend, but it is clearer trend shows in the calcite trend. So basically, the more the NCG that we inject, the more the calcite that will dissolve. And this is just for another minerals. So pyrite basically showing precipitation near the reinjection wells, but it is not clear trend difference from different NCG injection scenarios. So that is for 1D radial model that we can get the conceptual, and we can continue to the 2D models. So basically, we created 2D models with the similar parameters what parameters that we use in the 1D radial model, but the difference is we created such as a cross section from the injection wells in NM9 and NM8 to the NM7 production wells. It is the nearest production wells to our NCG injection in Ngatamariki. So we still use the same mineral assemblages from the 1D radial model, and the difference is only where we assign the injection and production rates. So this is the construction of the model, and this is the focus area of the model. This is NM9, NM8 reinjection wells, and this is NM7 production wells. So to create this model, we use same rock properties with what currently Mercury used in their model. So they use a double porosity here. We also use same criteria for this rock in this model, and then also other rock properties such as porosity, permeability, and others. And then what is the main difference between this model and the 1D radial model is where we assign the production and injection rate. So we assign in each of an individual grid here different production rate and also injection rate, and also different production rate here in the NM7 following the feed zone depth and also feed zones properties of each well. So now let's take a look at the results. So overall, the result is similar with what we saw in the 1D radial model, but with much more clearer differences between each NCG injection scenario. So first of all, I would like to show you the difference through times of example of porosity. So we created model since before NCG injection until the future scenario. So this is the condition before NCG injection scenarios for the scenario 25%. And as you can see, without the NCG injection, the porosity is already increased near the injection wells. And then if we inject the NCG to 2024, the porosity increase is enhanced. And if we model through the future scenarios in 2034, the porosity enhancement is increased basically near the injection well here and here. And the question is, how about if we compare the between scenarios, between 0%, 25%, and 50%? So now I will show you. Now this is the porosity changes result for first NCG injection scenario, which is if we didn't inject NCG at all, 0%. So actually the porosity is also already increased near the injection wells. But then if we increase the NCG from 0 to 25, we started to inject the NCG, the porosity increase is more enhanced, showing a higher magnitude and also a wider area here and also here. And what about if we increase more the NCG into 50%? And if we compare between this picture and this picture in 25%, the changes is not really significant because the trend in the changes in the mineral is not significant also. And then how about if we look at each of the minerals, mainly calcite, anhydrite, and pyrite? So this is the result for calcite. In 0% scenarios, the dissolution already happening in calcite. But then if we increase the NCG injection into 25%, the dissolution shows the model shows more dissolution trend here in near NM9 and also here near the injection wells. And then if we increase NCG more into 50%, the dissolution is is more happening near the NM9, showing by the blue color here and here. And also compared to the dissolution trend, there is also a small precipitation here in the upper part and also a little bit in the outer area of the injection wells. That is for calcite. And then for anhydrite shows a similar trend in 25% here in the next slide. It is showing more dissolution of anhydrite, but the difference between anhydrite and calcite is if we increase NCG to 50%, there is no significant changes between 25 to 50% related to the anhydrite dissolution. And the last one is related to the pyrite. So pyrite is precipitating near the injection wells here and here in small amount. And if we increase the NCG into 25%, we can limit the precipitation of pyrite here. And then if we inject more NCG into 50%, the changes is not that significant. So basically, if we inject more NCG, especially from 0 to 25%, we will get the more dissolution of calcite and anhydrite, and then we can limit the precipitation of pyrite. So as the conclusion of this research, the NCG reinjection can cause an increase in porosity and permeability, especially near the reinjection wells. And there are 3 minerals that is showing a significant changes, such as calcite, anhydrite, and pyrite. And in the 2D model, we can differentiate between the trend from if we increase NCG from 0 to 25%, it is showing a widened area of porosity probability increase, calcite and anhydrite dissolution, and also we can the model showing reduced precipitation of pyrite. But then if we increase the NCG more from 25 to 50%, we still get more dissolution of calcite, but without significant change on porosity, permeability, and other minerals. The future work of this research would be to incorporate the variation of mineralogy and then to use other EOS of TAF-REACT and maybe other modeling program to know better about the NCG breakthrough possibility towards the production wells. And the last one is to develop a 3D model. So this is the acknowledgement that I would like to say. And thank you very much for this opportunity.
Thank you so much, Mika. I see some of the questions, but maybe it's better to complete the WebHub's presentation, then we can take the questions.
Okay, I will stop share and give it to Pai. Please, Pai.
Okay. Let me share my screen. Can you see my screen? everyone?
Yes, we can.
Okay. Okay. So, kia ora, everyone, and good morning or good afternoon to everyone, depending upon the location, wherever you are. So the topic of my today's presentation is reactive transport modeling of NCG reinjection at NAFA geothermal field. I'm Vaibhav Rajput, and my supervisor is Dr. Ailan Kaya. Just a bit of introduction about me. So I'm originally from India. I've done my bachelor's in chemical engineering and master's in petroleum engineering. After that, I worked in India as a reservoir engineer for a few years. And just like Mika, a couple of months ago, I finished my Master of Energy here at Auckland University. So coming back to the topic, as we all know that NCG is co-produced along with geothermal fluids naturally when we produce them, and the average carbon intensity of geothermal fields here in New Zealand is about 64 grams of CO2 per kilowatt hour. If we talk about NAFA geothermal field in particular, uh, it is very unique because it is the only high temperature resource outside of Taupo volcanic zone, which is the primary geothermal location in New Zealand. This NAFA field started production or operation in 1998 with 10 megawatts, and its operational history can be divided into stages. Right now, it is producing about 50 megawatts of energy, and currently it is in consent application process to increase that production to 75 megawatts. If you look at this figure, which Alam had also presented, you can see on the right, we have NAFA, which has, among the geothermal plants, it has very high carbon intensity. And there was a risk that the plant could be shut down due to government regulations. And NAFA's response to this was to retrofit the plant so that it can re-inject the produced NCG back into the reservoir where it came from. And recently, it became the first geothermal plant in New Zealand to achieve the net zero status. Essentially, it is reducing about 128 kilotons of CO2 emissions annually. But still, there's some questions that are unanswered. The primary among them is what will happen to the reservoir properties once this NCG reinjection takes place. So essentially, what we're trying to answer over here are three key questions. First one is what are the changes to reservoir properties like porosity and permeability? What will be the total mineralization potential? Essentially, we want to know the fate of re-injected CO2 and H2S. And finally, we want to reduce the uncertainty in fluid-rot interaction effects due to the NCG reinjection. And as my colleague Mita has already explained, we are tough react is used in this study. And we know that tough react is a combination of tough2, which is a flow industry standard geothermal flow simulator, and chemical reaction. So it essentially solves the flow equations and the chemical reactions sequentially in the same iterations. And so that is how we try to model the reactor transport modeling. Over here, I would like to explain a slide about MINC. Some of you may not know what MINC is. So its full form is multiple interacting continua. In geothermal fields and also in petroleum fields, we have fractured reservoirs. So fractures is where the fluid flow takes place primarily, while the matrix acts as storage. Now, if we do it only with a single porosity, it would be very hard because we will require huge number of grid blocks to model the reservoir, to model the fractures properly. So one way to get around this is to use MINC. So essentially what we do is we consider that all the fractures are in one continuum. They communicate with each other, while the matrix can be one or multiple continuum. And specifically for NAFA, the fracture density is very high. It is about 15 fractures per meter. And the MINC approach is very appropriate for NAFA. And this is what we have used for modeling. Now, if you look at NAFA, there are a few production and reinjection wells, but we try to focus more on particular reinjection well, which is NG11. So now, if you look at the stratigraphy setting of NAFA, we have a reservoir and basement layer, which is highly fractured and which is made of brachiated grey-work argillites. It has a thickness of about 2250 meters. Above that, we have caprock, which is made of tertiary sediments, essentially brachiated siltstone, coarse siltstones, sandstones, and it has a thickness of roughly 500 to 600 meters. But since we are focusing in this 1D model on NG11, this is how the temperature and the pressure conditions look like. So for the feed zone depth, the temperature is around 223 degrees Celsius, the pressure is around 93 bars, and the main feed zone thickness is about 80 meters. Before operation started at NAFA, there were different wells drilled in the field to estimate the geothermal potential. And some of the authors conducted scanning in electron microscopy, SEM, and X-ray diffraction studies on these core and drill cutting samples. And they analyzed the mineralogy for NAFA, which is shown in this table over here. The mineralogy can be divided into caprock mineralogy and reservoir. For now, we are interested in the reservoir mineralogy, and you can see that it mainly consists of quartz, calcite, chlorite, feldspar, epidote, etc. For NG11, the well that we are focusing, we took about 9 primary minerals and about 8 secondary minerals from that were reported for this study. Now, the 1D radial model, we modeled about 20 kilometers of distance, out of which the first about 5.5 kilometers from the reinjection well was considered as MINC zone. So we have double porosity, fracture and matrix. And the rest 14.5 kilometers is the reservoir zone, which is single porosity. We use 100 grid cells, and we consider 3 reinjection scenarios. The first one is the base case. So even when we don't do active reinjection, there's still passive reinjection which is happening. So we took about 18% of NCG, which is reinjected in passive case. And then we also model 50 and 100% reinjection cases. Now, coming to the results, I'll just show results for few key minerals which had profound impact on the overall output. So first one is calcite, which we are really interested in because the injected CO2 is directly correlated with carbonates such as calcite. And now we can see that with addition of NCG, the calcite dissolution increases with time, and it can be seen in the graph on the right also. So essentially, what we also saw is that the injected CO2 and the dissolved calcite, it increases the bicarbonate concentration in the fluid, and essentially all the CO2 that we are injecting stays in the aqueous form. So this is one of the key output that we got. The other mineral that we are really interested in is pyrite, because as we know, H2S is one of the reactants for pyrite. And over here, what we saw is that in pyrite was precipitating. Essentially, the H2S that we are injecting is converted into pyrite, into mineral form, in solid form, and it precipitates. But over here, the passive reinjection case produced the highest precipitation for pyrite, and the lowest precipitation was observed for the 100% reinjection case. And overall, if you look at the mineral assemblage, we saw that since calcite dissolution was really high as compared to other minerals, precipitation or dissolution, the overall effect was that porosity increased from the reinjection well till about 150 meters, if you see on this graph. And then there's a small amount of precipitation from 100 to about 500 meters. So as we increased the NCG content from 18% to 100%, the porosity and consequently the permeability also increased. So this was one of the important observations. And then we also did some sensitivity analysis. We had a few parameters for which we thought had the largest uncertainty. The first one was calcite reaction rate. So essentially, when we model reaction kinetics, we can consider a particular mineral to be reacting at kinetic or at equilibrium. So over here, the base case we considered was at kinetics for calcite. But what if we had calcite reacting at equilibrium? So in that case, we saw that calcite was completely dissolving in that case, and it again, the distance was less than 100 meters to, let's say, about 50 to 60 meters from the reinjection well. The next thing that we tried to understand was reactive surface area. So as my colleague Mika explained, reactive surface area is one of the parameters which the engineers use to calibrate the model. If they have laboratory studies, they use this parameter to match the experimental data. But over here in the field case, unfortunately, we don't have that data. So we wanted to estimate what effect will this have on the mineralogy assemblage. So in this case, it was observed that calcite, elite, and albite were mostly affected by this particular change in reactive surface area values. And also in the literature, the iron and aluminum ion concentration were not reported. So, and as we know that Fe is one of the primary minerals, primary ions for pyrite reactions. So we wanted to estimate what effect will these concentrations have on the reaction kinetics. And it was found that pyrite, elite, and albite were mostly affected by these concentration changes. We also tried to do sensitivity analysis for a flow rate and fluid diffusivity between matrix and fractures, but they were not found to have large enough effect as compared to the previous three parameters. So right now, we are currently working on a 2D model. So we have got an idea of how the reaction kinetics and the mineralogy would change when we inject NCG from 1D model. But a clearer picture would be obtained when we set up a 2D model with all the major production and reinjection wells. We are also considering a flow from bottom cells. And essentially from this 2D model, what we are trying to answer are the questions related to flow effects between various production and reinjection wells. What is the hydraulic, whether these will have an effect on the hydraulic connection between wells, and how will it impact the mineralogy changes, whether the injected NCG will break through at the production wells, and possibly if there are surface leakages, we would like to answer those questions also. So coming to the conclusions, with this study, we found that calcite dissolution is very dominant for all the three cases, and the dissolution increases proportionally with NCG content. As calcite has a larger effect among all the minerals considered due to decrease in calcite volume, porosity increased, and similarly permeability increased near the near the reinjection well. Again, the mineralogy changes were mainly concentrated within a couple of 100 meters from the reinjection well. And the injected CO2 stayed in the aqueous phase throughout uh, the cases that we considered, while H2S partially precipitated in the form of pyrite. And among the sensitivity analysis parameters that we considered, the calcite reaction rate and the reactive surface area changes were found to be the most important in terms of mineralogy changes. And finally, I would like to acknowledge the University of Auckland and the Department of Engineering Science and Biomedical Engineering for funding this study. These are the references that I used. Thank you for your time. If there are any
Thank you so
questions.
much, everyone, for all your attention and for the great questions. So I can see some questions on the chat box, and I can start with one of them. It's Avata Postgrado U Virtual. A question for Elam. What type of outreach activities did you do, in particular with the Maori community? That's a great question. In New Zealand, we cannot even write a research project if we are not in good collaboration and communication with Maori. Especially geothermal is particularly very important for Maori. And in our project, Maori is we have a really deep partnering approach. They are our partners. They are our kaitiaki, which is guardian of the earth. They are stakeholders, our strategy formers. I mean, we design the work, whole project with Maori, and we have a dedicated Vision Maturanga teams. Vision Maturanga means Maori science. So we don't only look at with our perspective of science, because Maori have a different, deep understanding of natural process, and we are. I mean, they contribute with their Maori Vision Maturanga lenses. So our Vision Maturanga team involves trust owners like Aroha and Aroha Campbell and Andy Blair. Also, we have lawyers like Loretta. So they communicate with the community, and also they communicate with the regional councils in order to contribute for the policy makings as well. In terms of additional outreach, we promised in our project that we are going to get at least one Maori PhD student, but it is kind of impossible especially in the University of Auckland. A number of PhD students with the indigenous Maori origin is quite rare. So we are planning to go to high schools actually to encourage students to come to university first, to engineering first, then they can contribute to PhD positions as well. The Maori community is quite willing to take more part on the geothermal workforce because it is quite important for them. It is sacred. Also, in terms of commercial and economic way, it contributes to society quite important way. So we are in good contact, but we still need to do a lot more. I see our colleague Bettina Way is also here. So we are planning to make a website design, and we are planning to have a Maori version of that outreach as well. So this is what we are planning to do in terms of outreach. Mika, can you see the questions?
Oh, yes. So the next question is for me, I think, related to how did I measure the chemistry of the NCG feeding the model. So I got the chemistry model from Mercury. Mercury gives a lot of support related to the data and also to the discussion. Thank you very much. And related to how the chemistry is sampled is we in the methodology I explained that we use two fluid chemistry. The first one is related to the production the produce chemistry, that we get it from the NM7 production wells, and then this chemistry data is important because this produce chemistry fluid, then we must correct the condition to become the reservoir condition, and then we can input this reservoir condition chemistry into tough react. And then the second one is related to the injection chemistry. So they sampled the fluid in their brine line to know the fluid chemistry, and then however related to the how much NCG that they inject is is calculated from the mass balance calculation based on the how much steam that goes into the unit and how much NCG is produced. I think that is oh yeah, related to the scaling. Yeah, related to scaling, it is very interesting that there is one of the nearest monitoring wells, NM2, that I show you in the maps, located near the injection wells. In that injection wells, sorry, not injection, in the monitoring wells, they found in their recap tube an anhydride scaling. And it is also showing in our modeling, both in 1D and also 2D, there is a little bit precipitation of anhydride in the near the injection wells, if you remember, and it is correlated with what they found in NM2 monitoring wells. They also found anhydride scaling. And if the composition of the NCG is different, could we expect a different behavior in the porosity increase? I think yes, because when we model different NCG injection scenarios between 0, 25, and 50%, the trend of the porosity a little bit gives us a little bit different trend, especially between 0 and 25%. But in 25 to 50%, the porosity change is not that different. So there is like a limit. Now, if I can continue to the next question, which geochemical database did you use for your modeling? I think I used uh, the database from ThermoDDM, but it's already uh, uh, a lot of modification done in that database from the previous researcher in University of Auckland, and also from Elam. And next question is yeah, I think that's all for.
I think the next question is for Vaipal. Thank you, Mika.
Right.
Oh yeah, thank you.
Okay, so question is about surface leakage. Would it be the NCG leakage due to incorrect issues with the reinjection? And what the leakage refers to. So when I say surface leakage, we're injecting NCG at this point, and we know that there are some surface features in the geothermal NAFA geothermal field. It is possible that the NCG that is reinjected could travel back to the surface features via fractures. These surface features are there because they are connected to the deeper fluids via fractures, vertical fractures. And if we don't monitor the NCG that we are injecting, the composition at the surface features could increase. And that is what we are trying to model. So if in the 2D model, if we vary the permeability of the cap rock, do we see these this enhancement of concentration of CO2 and H2S at the surface blocks? That is what we are trying to model. And we also know that when we re-inject, when we increase the NCG content, it has an effect on the boiling of the fluid inside the reservoir. So there will be shift in the boiling temperature and pressure. And in the future, so that is what we want to know. Right now we are using EOS1, equation of state 1. package in Tough React. In the future, we would like to use a more advanced version like EOS2 or ECO2N, which would capture these effects more correctly, and we could answer those questions more properly in the future. So I think that is there, and so
Thank you,
I
Vipul.
guess right.
I see one more presentation from Jessica. A good presentation. I'm wondering how the chemical and geochemical model can be scaled up for field applications. This is a great question, Jessica. Yeah. So Mika and Vipul, they started with 1D radial models just to set up just to see what's happening around the injection valve. And then later on, they expanded their models to two-dimensional models. So which includes the interconnection and hydraulic communication between production and injection wells, or injection well and other reinjection wells as well. Because 1D or 2D models are not really very adequate to represent whole structure. You are injecting from one well, for example, and your model has closed boundaries. They cannot have the interaction between other wells as well. So the best way of doing this is your suggestion, actually, setting up three-dimensional numerical models. But those reactive transport models are extremely costly, because in terms of numerical process, at the moment, we need to use supercomputers. So we need to, we have some clusters which can utilize thousands of CPUs at once. So it speeds up our process, but still the computationals takes quite a bit of time and effort. And it includes lots of uncertainty as well, because you are taking some samples from underground in terms of mineralogy, but it doesn't represent the whole structure. I mean, in flow models, we have some uncertainties. We are not really exactly, we don't know exactly porosity, permeability, but in terms of reactive chemistry, the unknowns are huge. So that increases the load of uncertainty as well. But it gives lots of good clues, because up until now, we ignored the effect of thermal alterations and changing in the flow dynamics. So we are in that process. I mean, we developed some three-dimensional numerical models, but they are in theoretical ones. That they are not really they are representative to geothermal systems, but they are not specific to one geothermal system. So Mika is starting to his PhD soon, and we are planning to do a three-dimensional model for Natamariki, hopefully. Yeah, so this is going to be our start for three-dimensional models. Thank you.
That's good. Actually, I have another question. Sorry, I'm gonna ask very quick. How many grid cells have the 2D, and how long lasted in running?
Mika, do you want to answer, or Vipul?
Just for knowing, because it's very good to know where we. So in which point of time we are talking of the simulation time?
So yeah, related how much of grids, I think I haven't calculated, but I created maybe around 15 to 20 layers and I created the distance of each grid is around 50 meters. And then yeah, but how much grid I think I will need to check. But
Okay,
the
that's
time
okay.
for
That's okay. Don't worry.
Yeah, no, sorry. But the running time is actually very fast. Maybe only several several seconds.
Okay.
Below
Okay.
1 minute. Yeah.
Okay. Thank you. Good presentation.
Yeah. Thank you.
I think they are perfect in terms of timing, Daniela.
Yes, great. It was perfect. No, thank
It's
you
Auckland.
again. Yeah, thank you. It's a really interesting work, and really interesting to see how you can change and increase your model from one dimension to 2 dimension, and maybe in a couple of years we'll see the result of the PhD of your students with the 3D model. We can organize a new webinar with a 3D model. And no, thank you everyone for attending this webinar. We should have another one maybe in October from Portugal. So I just invite you to follow our LinkedIn account, the IGC project, and if you want to listen to previous webinars, also you can check the YouTube channel. And thank you again, Elem, and your
Thank you
students
so much
too,
for inviting
joining.
us. Yeah, it was a great
Okay.
opportunity to meet you all as well. Thank you.
Yeah,
Yes,
Have a great
thank
day.
you.
Thank you
Bye.
very much.
Thank you.
Bye.
Great
Thank
to
you.
see you all.
Bye-bye.
Great to see.